Welcome to Simple Harmonic Motion. Today we're going to talk about that and specifically masses and springs. Now what defines simple harmonic motion is you've got this restoring force. Well, first of all, with the mass spring, let's say we've got a mass hanging from a spring going up and down like this. What defines simple harmonic motion is the distance that mass is from its equilibrium position is directly proportional to the acceleration and the force on the mass. So if you double your distance from your equilibrium position, you double your force. We'll find out later that other types of simple harmonic motion have this similar idea where the second derivative of the position or something like the position is proportional to the position itself. So let's talk masses and springs. So focusing in here, if you've got a mass spring system, you've either got it horizontally, so you've got some wall and some spring and some mass hanging from it, and you pull the mass in one way and it goes back and forth, or you've got a mass hanging from a ceiling and you pull it down and it goes up and down. So that's kind of the spring version of simple harmonic motion. In this case, the net force is equal to your spring force. Your net force is m times a. Here's just another way of writing a, as you know from your calculus class, the second derivative of your position. And that's going to be equal to your spring force, which remember is equal to negative your spring constant, which is kind of like how stiff the spring is, newtons per meter, how hard it is to stretch or squish, times how far you've stretched it from your equilibrium position. And the negative is just here to say that, hey, if I pull this mass to the right from its equilibrium position, then the acceleration and force will be to the left. So your acceleration is in the opposite direction to the displacement. So that's what's going on there. If we rearrange it, we end up with the second derivative of position is equal to minus k over m times the position. Now this might look kind of familiar, like what kind of function do I know where if I take the second derivative of it, I get kind of negative times my original function. So let's take a look at that. So yeah, that sounds like sine or cosine to me. So what we're going to do, it's a bit of a jump. Let's assume that, hey, it's some sort of sine function. Now it's going to be modified. It's going to have some angular velocity, just determining how long its cycle takes. And it's going to have some amplitude. That depends on how far you pulled it initially. So this is kind of like your max displacement, sine, and then some form here, an angular velocity that tells you how long it takes to do its thing, how long it takes to do a cycle. Now we're going to use sine if at t equals 0, it's at its equilibrium position, because sine of 0 is 0. But if it starts out fully pulled back, which it will a lot of the time too, we're going to use cosine. It's going to end up not mattering a ton either way. It's just kind of pick which one matches your starting conditions. If it's fully pulled initially, we'll do cosine, because cosine is 1 when it's 0, when t is 0. And if you're starting at the equilibrium position, it's already moving, we're going to use sine. In university, it's going to look a little more like this. You're going to be like x equals your amplitude times sine or cosine times your angular velocity times time plus some phase variable, phi, where it's just the phase. It's just some constant you throw in so it it matches your initial state, because that way you can deal with not just, hey, it's at the equilibrium position, or hey, it doesn't just start fully pulled back, but you can handle anywhere in between if you want. Anyway, that's all this junk is. It's a constant. It looks scary. It's not that bad. So all we got here is we are guessing our function given that our second derivative is equal to some junk times negative our original function. That sounded like sine or cosine, so we're going to assume that. We're going to be like, hey, there's going to be some amplitude that's just its max value, how far you originally pulled it back, and there's going to be some angular velocity that determines how long a cycle takes. All right, so working from that assumption, we're just like, hey, our x position, our distance from our equilibrium position is our amplitude times sine of this angular velocity times t. We can take the derivative of that. It's just derivative with respect to time to find velocity. Notice this angular velocity comes out because of the chain rule, and sine has become cosine. So now it's this angular velocity times a cosine omega t is our velocity. So that's not much harder. And then we can take the derivative again to get acceleration. If we do that, we get another angular velocity term coming out again, and then this negative, because the derivative of cosine is negative sine. So yeah, this looks pretty similar. If we say, hey, our second derivative equals our second derivative, we can say, hey, before up here, we decided when we rearranged that our second derivative was equal to negative k over m times our original function, our original displacement. And with this, with our assumption, we're like, okay, it's negative angular velocity squared times the amplitude times sine omega t. So, if we cancel out our a sine omega t, we end up k over m is equal to our angular velocity squared. So we've just discovered that for all spring systems, your angular velocity is always the square root of k over m. And that will be super important and show up a lot. It's true for all mass spring systems. And now we can come up with a whole lot of information because of that. We'd be like, hey, well, angular velocity is just 2 pi over the period. That's just how it's defined. Kind of, you can think of it as sort of distance over time, or angular displacement over time. And one full cycle is 2 pi, and time is the period. So if we rearrange that, our period is 2 pi over the angular velocity, or the period is 2 pi square root of m over k. And it became m over k instead of k over m just because we divided by it, so that kind of flips it. Yeah, so think that through. Just sub this in right here, and you'll find this lovely formula, which is also on your formula sheets, which is useful. You might also need to solve for frequency sometime, and if you remember, frequency is just 1 divided by the period. So if we just do 1 divided by our formula for period, we end up with this lovely guy, which is same thing but flipped. And that's it. There's a couple other things we can do to find our max displacement and our max velocity and our max acceleration. If we go and take a look at this, initially our maximum displacement is amplitude. That's how we were defining it before. But if we think about it here, notice I'm just assuming we started with sine. It's the same idea for cosine. Anyway, the max value that our velocity formula can take is a times square root of k over m. So notice your velocity maximum will always be your max amplitude times the square root of k over m, your angular velocity here. So that's just defined. That will always be the case for a mass spring system. And if we do this again, you'll find out that the max value acceleration can take is your max displacement times k over m, or max displacement times your angular velocity squared. So that's this guy here. So keep this guy in mind. Notice it follows pretty obviously once you know that this is your formula for position. If you take the derivative, you'd be like, hey, this is the max value this formula can ever be. And hey, this is the max value my acceleration can be. So it follows pretty naturally if you know that this is the formula for position, which hopefully makes sense now. One thing that comes up a lot in the questions is all these formulas. Notice there is zero dependence on the acceleration of gravity. So if you take a mass spring system to Mars, if you take it to the moon, it just doesn't matter what the acceleration of gravity is. That is it for mass spring systems. I hope you had as much fun as I did. Stay healthy and study hard.